Okay, there are no more people for now in the waiting room. I think we can start recording our lecture. So good afternoon all. We are a bit minutes in late. It's not a problem. Waiting for more participants for now. I will leave the floor to Professor Gabriel Pavel for his first lecture this afternoon, as said before, about the CANDU reactor concept and engineering. I'll go on admitting people while Professor Pavel can start presenting his presentation. Gabriel, please, the floor is yours.
Good afternoon, everybody. Do you hear me?
Yes.
Okay, great. I hope you enjoyed your lunch. Mattia, should I wait a couple of more minutes? What do you think? Or should I go?
Okay, just 1 second. Yes, everyone, we can wait. People is joining
okay.
Slowly, but they are coming. I mean, I think we can wait till 5 minutes, 2 minutes more.
So 5 minutes.
Okay.
It's gonna be enough.
No problem.
In the meantime, I see here on the schedule that I will be followed by Professor Zieberth, which is presenting the generation 4, so quite a leap between these generations. So I think it's going to be interesting to observe the main differences between them. CANDU reactor is kind of an old generation reactor. Nowadays, people are speaking mainly of small modular reactor or generation 4 reactors. So let's see how it goes. In principle, I will structure my presentation today into several, let's call them several stages, because, well, in fact, the time is very limited, and I would like to give you an overview of what, in fact, it's a CANDU type reactor. Not many of you, maybe not many of you heard about it or know too many things about this type of reactors, mainly because if you're coming from Europe, in Europe there is only one, or in fact there are 2 reactors in only one place. So Europe has only one nuclear power plant which with such types of reactors, such type of reactors. Okay, looking at you. Okay, I think I can start.
Yes, okay.
Okay. Let me start sharing my screen. Mattia, please let me know if it's everything good. Do you see my full screen or is it?
Yes, perfectly. You can
okay,
go.
great. Let me try to hide you because my screen is covered with your names. Okay. So, CANDU or Canada deuterium uranium. This is a type of reactor, which was built a long time ago or designed long time ago. Again, this is my presentation today. So a short overview, a history of the CANDU reactors, main design features, a short explanation of how this reactor operates, a quick overview of the fuel cycle and fuel particularities, mainly focusing here on particularities. You will see that the fuel cycle, in fact, it's not quite complex, rather the opposite. Again, okay, and heavy water. I choose to have a separate chapter for heavy water because this is a particularity of this reactor. And also some, well, not some, but a very short overview of the main safety systems. Okay, CANDU overview. In principle, okay. How do you recognize when you see a schematic of a CANDU reactor? You can easily find it, or you can easily find out which one of the reactors, it's a CANDU type reactor because it's placed horizontally. In principle, this reactor looks like a huge pipe which is placed horizontally. One other important factor or one other important piece of the reactor is that it uses pressure tubes. So if you look at the PWR, pressurized water reactor, the CANDU reactor, which is a pressurized heavy water reactor, it uses pressure tubes against pressure vessel, like in PWR. For heat removal, it uses two separate systems, like the primary circuit, which deals with the the nuclear region of the reactor, and the separate system, which deals with the classical part of power plant. I'm not saying nuclear power plant because the classic part of a nuclear power plant is similar to a normal power plant, like a coal or like gas or whatever. It features the CANDU type reactor. It features also two safety shutdown systems, which are fully independent, and from the conceptual point of view, they are totally different. So for the safety reasons, these safety systems, these shutdown systems, are completely different. An important particularity of this reactor is that it uses natural uranium as fuel. So no enriched uranium, but rather natural uranium. The difference between natural uranium and enriched uranium is the following. When you have natural uranium, the enrichment, let's call it like this, it's only 0.7, around 0.7% of the uranium-235 isotope. When you go to PWR, sometimes you use 3 times this figure. So almost 3 times this figure. Also, another particularity is that this type of reactor uses heavy water. Maybe you have heard from my, let's see. Okay, no, you haven't heard yet. Maybe from school, but not from us. It looks like the PWR type reactors are using light water. Instead, CANDU reactors are using heavy water. You will see later which is the difference between these two types of waters. Okay, a very short history of the development of the CANDU reactor. It all started just a little bit after the World War II with the ZIP reactor, which was developed in Canada in 1947, if I'm not wrong. I think the first connection to the grid or first operational set point of the ZIP reactor was in fact in 1945. After this first generation, as a normal follow-up, the second generation of the nuclear power plants or of the CANDU type reactors appeared. And this is the 600 megawatt electrical megawatt reactor, which kind of the first one, the first unit, the Pickering A unit, was connected to the grid in 1971. Nowadays, this second generation of CANDU type, it's installed in Romania, for example, because now we're speaking about Europe, and the 600 megawatts turned into about 700 megawatts. These two generations were followed by other generations. The third one would have been the 900 megawatts, which is not on the market, and the fourth one being the advanced CANDU reactor with advanced CANDU reactor 700 and 8000. They were never built. These kind of units were never built up to now. Okay, today you can find throughout the world about 31 units. So 31 CANDU type reactors, to which we can add about 16 Well, conceptually, they are very similar, but these 16 reactors, it is said that it's Indian Kandu type reactor. So it derived from the original Kandu reactor. The original Kandu reactor was developed by AACL, an Atomic Energy of Canada Limited, and of course, Indian. I have no idea who developed the Indian reactors. From the design point of view, as I said, you can, when you are speaking about Kandu type reactors, you can imagine a huge pipe filled with smaller pipes. That's the best way to identify a Kandu type reactor. This huge pipe is housed in the reactor vault. This huge pipe, it's called the calandria vessel. So we have a calandria vessel, which kind of functions at normal, almost normal pressure, and which is filled with water, but not any kind of water, but rather heavy water. Heavy water as moderator. Again, inside this huge calandria vessel that functions at almost normal pressure and temperature. Normal meaning close to the what you see outside. Normal pressure meaning almost the atmospheric pressure. But when it comes to temperature, just think of it as a very hot summer in Spain, for example, or maybe in Africa, because there are about 70 degrees there. Now, this huge pipe is housing smaller pipes, which are called calandria tubes. And inside these calandria tubes, which again, they are placed in the moderator, functioning at very low parameters. Inside these calandria tubes, you can find the pressure tubes. As they bear the names, the pressure tubes are the tubes that support most of the efforts, both in terms of pressure and temperature. So inside the pressure tubes, we have increased pressure, increased temperature, increased parameters. So I told you about the moderator. The shutdown system number 1. Sorry, the shutdown system number 1 is represented by this. I don't know if I can have a pointer. No, I don't think I can have a pointer. Oops. Okay, some characteristics here. I will just give it to you. So the shutdown system number 1 is represented by these rods. So these rods, the role of these rods is to completely shut down the reactor in case of emergency. So they simply drop. We have about 28 pieces of each, and they simply drop inside the reactor. The completely different shutdown system is the one which is called shutdown system number 2, and which is represented by a liquid injection in the reactor. When it comes to power, the 600 megawatts, which are electrical megawatts, are translated into about 2,000 thermal megawatts. So the thermal output of the reactor, it's about 2,000 megawatts. There are, as you can see here, these tubes have something connected to them. These are headers, either inlet header or outlet header. Inlet means that something comes inside the reactor, and that something is the heavy water. And outlet header is represented by the water, again, heavy water, which exits the system. The normal operating temperature of the inlet header, it's about 260 degrees, 266 more precisely degrees. The outlet, so after the water was heated, it's about 316 degrees. And let's say the operating pressure, it's about 10 megapascals. The coolant flows with about 24 kilograms per second, if I'm not wrong. And Another particularity of this reactor, it has two loops, in the sense that half of the reactor is has assigned one loop, and we will get back a little bit later to this, and the other half of the reactor has assigned another loop. Okay, all these details, I will not insist on these details, but you can find them here, so I will leave them to you. Whenever you wish to have them, you feel free to use them. Okay, how it operates. Okay, this is simply put it. You see here the electrical grid, the grid that helps us getting the electricity. You see here the classical part of the reactor, which consists of a steam turbine. Then we are moving to the nuclear part, and the first thing you will see here is the steam generator, and this you will see the steam generator with two colors. Two colors meaning, in fact, two things. First of all, the hot water, which comes from the, as I said, this is the reactor, is placed horizontally. So hot water provided by the reactor core, which enters the steam generator. So consider that one half of the steam generator is very hot, and the other half is kind of cooler, because this part, which is with light blue, is the part with the water that takes the heat from the water, the heavy water from the reactor core, and transforms it into steam, which goes into the turbine. I said that there are two colors because of the two reasons. One, very hot, and then cooler. But the other part of what I wanted to say is that half of the steam generator is filled with heavy water, which comes from the reactor, and the other half, because there are two different loops, the other half goes normal water, demineralized water. Okay, moving forward, this is the control room and the fuel management facilities. I will not insist on these two. Good. How does this operate? You see here, in fact, there are 4 steam generators and 2 identical loops. Half of the reactor has assigned one loop and the other half the other loop. So you can have 380 fuel channels. Half of the 380, so 190, are assigned to 2 steam generators, 190 are assigned to the other 2 steam generators. All the steam generators are designed to withstand more than the normal heat capacity produced by the reactor itself. Okay, I need to speed up a little bit. The fuel cycle. In principle, you will see here a very important line, arrow, and this is starting from the uranium mine and going directly into the CANDU reactor, because the CANDU reactor uses natural fuel, and that's it. Of course, as I wrote here, the CANDU reactor is to some extent versatile, which means that it can accept other types of fuels. But if you wish, the initial design of the CANDU reactor was to use natural fuel, natural uranium. There are several fuels, the Dupik cycle, direct use of spent PWR fuel in CANDU. So after you use the uranium, the enriched uranium in the PWR reactor, you can, after reprocessing, you can use it in the CANDU type reactors. It can use also a thorium cycle fuel, but it also can use MOX type fuel. Okay, this is the fuel bundle. This is a fuel bundle. How does the fuel enter the reactor, or what is represented by this fuel? The fuel bundle has 37 rods. Okay, 37 rods called elements, 37 elements. This is the classical fuel assembly of CANDU type reactor. each one of these elements is filled with pellets, small pieces of uranium pellets. Okay, another piece of information, you have here the sheath material, which is zircaloy 4. It's an alloy which zirconium brings its properties to the table and gives the fuel bundles some special characteristics. These fuel elements are separated by some spacers, and towards the end, a grid, so they are welded to this grid, but also some spacers between those fuel elements are present. What's the purpose of these spacers? The purpose of them is to keep them distant, to avoid touching the fuel elements in case of something happens. Okay, so imagine, one other piece of information. Each one of these fuel bundle, it's about almost 50 centimeters long. So it has almost 50 centimeters long. Okay, imagine 12 pieces of these fuel bundles that are stuck into the pressure tube. So each pressure tube, as you can see in the middle here, has 12 fuel bundles. So 12 fuel bundles. The second point here, it's a very interesting separation of the fuel from the outer world, let's say. So we see here the fuel bundles are inserted into the pressure tube. This is the closest tube to the fuel bundle. Then this pressure tube is having inside, so inside the pressure tube you find yourself fuel bundles and of course cooling agent. This cooling agent is heavy water. Then around this pressure tube you can find the calandria tube. The calandria tube is the tube that I already said it functions at lower temperature, lower pressure. And around this every calandria tube you can find the moderator. Imagine this fuel channel that I just told you about. We have 380 of these fuel channels. I marked here, I bolded here the online refueling. This is the main characteristic of the CANDU type reactor. So each CANDU type reactor, let me see. Okay, this is a picture of the face of a CANDU type reactor. Each each one of these 380 tubes allows the fuel bundles to be changed during normal operations. So you don't have to shut down the reactor to change the fuel, which is kind of cool because well, ideally you can function with the reactor without any stop. In the reality, it's not like this because you also need to have some normal checks, normal shutdowns, operational shutdowns, where you check the things to see if they are working properly and so on. Okay, how is it done? The refueling is done by a refueling machine, of course. It's a machine that replaces the depleted fuels with fresh fuel bundles. So you have two heads, two similar machines placed on both sides of this huge pipe called calandria. Both of the machines are connecting to the same fuel channel. One pushes the depleted fuel, the other one retrieves the depleted fuel, but in the same time, when the first one is pushing the depleted fuel, it adds also a fresh fuel bundle. Weekly, we have about 10 fuel channels refueled with fresh fuel. The heavy water. Okay, heavy water in the CANDU type reactor is used in two different ways. First, as a moderator, and second, for cooling. Let me see. Okay, what is this heavy water? You know, you have most probably heard of the normal water, which has one molecule of hydrogen. Well, hydrogen has several isotopes. So this one of the isotope of hydrogen is deuterium. I wrote here that its mass is double that the ordinary hydrogen mass. So at the end, when you have H2O, like normal water, when you will have D2O, because hydrogen has deuterium has one neutron and one proton, you, instead of having the mass 18, 16 from the oxygen, 2 from the hydrogen, now you will have doubling the mass of the hydrogen, so you will have 16 mass of oxygen, with which you add 4 the mass of deuterium. This is why it is called heavy water. Okay, how to obtain the heavy water? You have, I wrote here, you have 1 atom of deuterium for every almost 7,000 atoms per hydrogen. So at the beginning there was this method to obtain heavy water, which is called continued electrolysis, but it was very expensive to have it, very expensive to support it and to have it. And then nowadays you can use fractional distillation, where there is a good part and a bad part. The bad part of this is, the good part of this is that you don't really need too much heavy water, because the reactor itself is not supposed to lose heavy water. And from this good part results the bad part. If you develop and build a facility for extracting heavy water, at some point in time you will find it very useless, because if the reactor doesn't lose heavy water, there is nothing out there that consumes the heavy water. So that's the downside of this. Okay, I wrote here heavy water as moderator. So besides the fact that the heavy water can subtract the heat, can remove the heat from the reactor, this heavy water is used also as a moderator. Why? Because you will see here 2 very important factors: neutron scattering cross-section and neutron absorption cross-section. When you hear about absorption, you mean you immediately in your head, you will imagine something that absorbs. Okay, it absorbs, but in the same time, the heavy water needs to scatter these neutrons. Why scatter? Because we need neutrons to have the famous fission reaction. Okay, what is the role of heavy water as moderator? As I wrote here, neutron moderators are used to slow down the fast neutrons. When we are talking about reactors, there are two major types of reactors: the ones that are using slow neutrons or thermalized neutrons, and the ones that are using fast neutrons. CANDU, it's a type that uses slow neutrons, or thermalized neutrons. This thermalization of neutrons is produced by this moderator. In our reactor is the D2O, the heavy water. Okay, and now I'm reaching the last slide of my presentation, the shutdown systems. As I said at the beginning, there are 2 conceptually different shutdown systems. One represented by 28 mechanical fuel rods made of cadmium. This is a very powerful neutron absorber, which are hanging outside the reactor, they are hanged by a system, a closed system, which is continuously powered up. In case of emergency, these claws are automatically released because of lack of electricity. So the electricity keeps these claws stick to the shutdown rod. In case of losing the power, there is no force that keeps these rods. So automatically, due to the gravitation, these rods will drop into the reactor and will shut down it by cutting the fission reaction. Another system, the secondary system, or the second system, is the shutdown system number 2, which consists of gadolinium nitrate. It's a solution, it's a liquid solution which is injected into the reactor to stop the fission reaction. So it is injected into the moderator, absorbs a lot of the neutrons. So instead of having this small absorption cross-section, you will have a huge increase in the absorption cross-section. But in the same time, you will not have scattering. Neutrons will not be scattered to meet another atom of uranium. So in principle, the fission reaction shuts down. It is shut down. In principle, this was my presentation for today. If you have any questions, I think I took almost all the time, but I'm happy to answer any questions you may have.
There is a question. Thank you, Professor Gabriel Pavel. There is a question in the chat from Marian. He asked, as you said, Candu can use different types
Marian.
of
Marian, you have did 4 years of can you please let the others have questions? Marian is my good friend from home.
And then also there is a question from Tobias. And
is the reactor usable after gadolinium injection? Only after you remove it. So only after you remove the gadolinium from it. Otherwise, the gadolinium will keep absorb the neutrons, so there is no fission reaction.
Okay, so then if there are any other questions,
so to answer, if I don't have another question, to answer Marian's question, yes, it is possible to use. There is a special fuel bundle, 43 elements fuel bundle, which uses enriched fuel, but it also contains in the middle. There is a fuel rod which contains dysprosium, a lanthanidic element, which is kind of an absorber. So you don't use purely enriched uranium, but you also use absorbers to compensate, well, to do many things, this absorber. But again, there is this possibility to use low, slightly enriched uranium. So no like in PWR. And the best part of it is that there is, when designing this new type of fuel, the designers took into consideration that this fuel bundle should be used in the actual reactor. So you don't need to buy or to build a new reactor to use this. The outer diameter is similar to the 37 one.
Okay, thank you, Gabriel.
Thank you very much.
Question now. So thank you again. And now we can move to the second lecture. I'm sorry. And it's now time for Dr. Mate Siebert to talk about the generation for reactors. And so Mate is already with us.
Yes, thank you very much. There was a slight change in the program. So in the latest version, I could see that first is my presentation about nuclear fuel cycle, and the generation 4 reactors will commence tomorrow. So this presentation will be a short, quick overview of the nuclear fuel cycle. I just share the screen. Okay, can you see my screen?
Yes, perfectly. We can hear you as well. So
okay, thank you very much. So, good afternoon, welcome everyone. My name is Mate Siebert. I'm an associate professor at the Budapest University of Technology and Economics, Institute of Nuclear Techniques. And in fact, I do research, I mainly do research in reactor physics. And in this research related to generation 4 reactor types, especially fast reactors, and how it influences the nuclear fuel cycle. So you will see that my nuclear fuel cycle presentation will be also focused a little bit on these issues, but we will go through the to give a complete overview of the fuel cycle. As usually, I'm happy to receive your questions in the chat, and I try to speed up to have time to answer your questions and comments at the end. So what is the nuclear fuel cycle? It's practically everything related to the uranium and the nuclear fuel fabricated from it, from uranium mining till the final disposal of the waste produced from the nuclear fuel. One characteristic of the fuel cycle that it is not necessarily a cycle. It becomes a cycle if you have reprocessing of the spent fuel and you have some kind of recycling in your fuel cycle. This is what we call closed fuel cycle. But an option can be also to go directly with the spent fuel to the disposal, and in this way we speak about open fuel cycle. So we will go through all these facilities and elements of the nuclear fuel cycle in the presentation, and we'll look into the different options with the so-called back end of the fuel cycle. We call the back end, which is after the reactor, and we call the front end, which is before the reactor in the fuel cycle. So let's start with the very beginning of the front end, which is obviously uranium mining. There are three important mining methods. Two of them, I guess, is very familiar to everyone from other kind of minings as well. So underground minings, when you have a deep shaft and reach in this way the uranium ore, and the open pit, when the uranium ore can be accessed from above, obviously with quite large environmental impact. But which is very important nowadays is the so-called in-situ leaching technology, when you pump in fact, the solvent into the layer when you have the uranium ore, and practically leach, so solve the uranium ore from there and transfer as a liquid up to the surface and produce in this way the processed uranium. This is very important because presently this is the cheapest way of uranium mining, and it's largely it's a large portion of uranium process nowadays comes from this technology. At the end of uranium mining, the processing, you got the famous yellow cake, which is a mixture of uranium oxide with this chemical formula. An important question is that how many uranium we have. On this slide, I noted with this line the different levels of uranium assets. What we call practically uranium assets are the so-called the identified resources. So those are the uranium resources where you have some actual evidence that it is there, and what is the quantity. This is around 7 or 8 million tons. It varies a little bit year by year, a little bit increasing usually. And you have about the same amount of so-called undiscovered sources, speculative or prognosticated. So based on the geological characteristics, you assume that there are some uranium there. It is also very important that the cost of producing the uranium is different. And nowadays we are in the age of quite cheap uranium, but as these resources will be consumed during the years, the price may go up because you have to reach more and more expensively recoverable resources. The green line here is that what happens if the consumption remains the same, and this is what we usually tell, that like it's 120, 130 years we have uranium to operate the reactors for sure on the same level that we have right now. Practically every forecast says that some kind of increase will happen in the nuclear production. Therefore, we can predict that these kind of resources can run out a little bit sooner, but it's still quite a long time. But if we consider a case, which is the World Nuclear Association suggestion, where we really very much rely on nuclear power in meeting the climate goals, then these resources can run out much sooner. So maybe there are it's worth to look into options how to increase the efficiency of the use of these resources. The next important step is so-called conversion. The only aim is to produce uranium hexafluoride from this yellow cake, because uranium hexafluoride is a gaseous substance. It's sublime from solid form to gas form around 50-60 degrees on atmospheric pressure, and we need this gas for the next step, which is the enrichment. In the enrichment, we know practically the most important three technologies are given here. The gaseous diffusion, which was the first commercial technology, but with a very low efficiency. Therefore, for nowadays, it's practically completely replaced by the centrifuge technology. These are all based on the small mass difference between the uranium hexafluoride with uranium-235 and the uranium-236 in order to produce an enriched steam in uranium-236. It's worth to know that there is a new technology, laser isotope separation, which uses the small isotope effect due to this difference between uranium-235 and uranium-236, and that uranium-235 can be excited a little bit more by a well-tuned laser, and then collect with electromagnetic force. But this is still under development. It's a big promise. It may change the enrichment market, but no industrial facility exists yet. Once you have the enriched uranium, you can fabricate fuel. Since the light water reactors uses enriched uranium oxide fuel, these are ceramic pellets of uranium oxide powder produced with high temperature sintering and filled into zirconium tubes, which is the cladding material again in thermal reactors. Now the interesting stuff starts when we irradiate this fuel. I put here as an example also when we use thorium and uranium-233 in the reactor, but we will focus on the so-called uranium-plutonium cycle. So the common nature is that you have so-called fertile isotope, and if this fertile isotope absorbs a neutron, then with a few, like 2 beta decays, a fissile isotope is produced. This is also true for the uranium-plutonium cycle. When the uranium-238 is considered as fertile, and with the very short half-lived uranium-239 and neptunium-239, finally, plutonium-239 fissile material is produced. But obviously, you have also the uranium-235 fissile material, and your reactor operates based on this. But during the operation, uranium-239 is produced in every reactor. This is this figure is to show what processes happens in a uranium oxide fuel. So in an enriched fuel, like typical enrichment is 4%, the rest is uranium-238. What happens that a large portion, like 3% of this uranium-235 goes to fission product, so fissions and produces energy. You have only 1% at the end of the cycle. But during the same time, from the uranium-238, about 3% plutonium is produced. And from this 3%, during the same campaign, 2% is used. So altogether, you have like this 5% of fission products, and 2% was produced from the fission of the plutonium. And obviously, the power is also very much produced in the same extent produced from plutonium. And at the end, in the fuel, you have the same about the same amount of plutonium and uranium-235, but you have to note that the plutonium has only 65% of fissile plutonium content, so uranium-239 practically, and also plutonium-239 and also 241. This process is called conversion. And now one option is, which I already mentioned, that this used fuel can be considered as waste and go to disposal. And this is what we call open fuel cycle. From this respect, I could go to the end of the presentation about the disposal. But let's see the other option when you do so-called reprocessing. So a chemical separation of the uranium and plutonium from the other components in the spent fuel. This is, in fact, in industrial practice, this is a well-established technology, the so-called Purex process. And the reprocessed uranium, you may re-enrich the reprocessed uranium and use again in the same way. And you can also use the reprocessed plutonium in the so-called MOX fuel. But the rest will go to the waste, usually in some kind of vitrified form. So let's see, what is the MOX fuel? We call it mixed oxide fuel because it's uranium plus plutonium oxide. And the fissile content of this kind of fuel is based on plutonium. So again, here you can see that like you need about 7% of plutonium because only 65% of it is fissile to produce the same amount of fissile material than with the uranium oxide fuel, and the rest is uranium-238. And then what happens during the irradiation? Again, from the 238, more plutonium is produced, while like 3% of this plutonium fissions. And what remains at the end is plutonium, but now only with 55% of fissile material. So obviously, as you may expect, the ratio of fissile material finally reduces in the fuel. And in fact, the problem is that this kind of plutonium cannot be used in thermal reactors, in light water reactors again. So this spent MOX fuel is not reusable with in the current practice. This is only a one-time recycle. This also happens in the industry nowadays, like in France, and like Japan has plans, but it's not happening right now. And there were other countries in Europe which did this, but not doing it anymore. So this is a so-called one-time recycling. And the problem is that the fissile material content decreases. You cannot reuse anymore. You cannot really recycle it again and again with this kind of technology. So what happens, I mentioned this conversion, and you can describe conversion with the conversion ratio, which is the produced fissile material per the consumed fissile material. And this is smaller than 1, as we could see in this case. But we can speak about breeding. The breeding ratio is the same, only we call it breeding when this number becomes larger than 1. So how is it possible that you produce more fissile material than what is consumed? Let's quickly have a look into it. For this, you need a little reactor physics or nuclear physics, that the definition of the fission neutron yield. So we need to calculate the average number of neutrons produced from one absorbed neutron. This you can calculate from the number of emitted neutrons per fission and from the capture to fission ratio, so from the fission and the capture cross sections. You should note that this the number of emitted neutrons varies with the energy of the neutron inducing fission, just as the same way as the cross sections. So if we look into this fission neutron yield as a function of the neutron energy, we got these curves for different fissile materials. And the model is simple. From these neutrons which are produced here, one neutron is needed to maintain the chain reaction. So this is one neutron. Then another neutron is needed to be absorbed in a fertile isotope and produce a fissile one. So you can, in this way, replace the fissile isotope, which was just lost. So, and also some small fraction of the neutrons are lost, are escaped from the reactor or captured in some structural material. So we can say that we need this mu definitely larger than 2 in order to ensure any kind of breathing, because that means that you both have the chain reaction maintained, and you always replace the consumed fissile isotope by a new one. So how is it possible? You can see that in the thermal range, it's only with the uranium-233 that it's slightly larger. So that relates to the thorium cycle, the use of thorium as fertile material. But in the fast neutron range, you can see the plutonium-39 with quite high values. So the answer is that you need fast neutrons and plutonium-39 as fissile material in order to be able to produce fuel breathing. So this table also emphasize this, that with plutonium-239 in a fast neutron reactor, you got the larger number of nu, which is really above, significantly above 2. The other cases are around 2, and also in the uranium-233, you have numbers larger than 2. So this is why the thorium-uranium cycle is also feasible. In fact, in fast neutron reactors, even breathing ratio of around 1.2 is feasible. And thermal reactors may run on the plutonium from fast breeders. And in such a system, you can multiply like up to 50 times the efficiency of the use of the uranium resources. And suddenly you have natural resources enough for 1,000 years, not for 100 years. And you may even diminish uranium mining. Another important aspect of the fuel cycle is that what kind of waste is remain after it. There are two main processes producing the waste. One is the producing higher actinides, which can be either major actinides, which is the uranium and plutonium, or the minor actinides like neptunium, americium, and curium. These are all highly radiotoxic alpha decaying isotopes, which form a decay chain. So in fact, their half-lives are not important, because even if they decay fast, they decay into another actinide with alpha decay and mainly alpha decay, and so a long decay change will lead only to stable isotope. On the other hand, fission products are less toxic because they have beta decay. They usually have, with a few exceptions, short half-life, and usually with 1 decay decays into stable isotope, or maximum with 2 decays. So if you look into the long-term risk of the high-level waste from the fuel, you will see that it is very much dominated by plutonium, and this is why it goes to the level of the uranium ore, so which is a kind of reference level, only after more than 100,000 years. Then the next important component are the minor actinide, and we are still above 10,000 years. And after that, what remains are the fission products, and with them we are well below 1,000 years. So if there is an option that we can remove, we could see that plutonium can be reused with fuel breeding, and can be used as a fissile material. And if we are able also to use the minor actinides, then we made a great advancement in reducing the long-term risk of the high-level waste. For this, again, the fast spectrum is an important, is very important, because if you look into the fission to capture ratio of some typical minor actinide isotope or actinide isotope, you will see that at high energies, all goes above 1. So fission is more likely than capture. And when with fission, these actinides produces energy and are converted into fission products, which are less toxic. So this is the basic idea of the technology that is called partitioning and transmutation. It's called partitioning because it needs an advanced reprocessing where minor actinides and fission products are also need to be separated. These need new technologies of separation, which are right now on a demonstration or industrial, semi-industrial scale. And the transmutation is that we transform the long-lived nuclides into short-lived by neutron irradiation. And here the main aim are the minor actinides, which can be burnt in fast reactors into fission products. Concerning the fission product, we have much less interest due to the lower radioactivity, and also for many of them it's not feasible. It's maybe the technetium-99, which could be feasible in with irradiation in thermal spectrum. So, but any of the options used, we need interim storage of the spent fuel after the reactor in order to reduce the decay heat before the final disposal. This is the main goal of interim storage. It can be either wet with large cooling ponds, or dry, either in containers or in special pits for each fuel, which is cooled by natural circulation. At the Paks nuclear power plant in Hungary, we have a similar installation than this so-called cascade facility. And finally, again, with all fuel cycle options, you have some kind of waste which needs deep geological disposal, either as a vitrified waste in the closed cycle, or as the direct disposal of the spent fuel in an open cycle. You have in these final disposals, you have to design several engineering barriers around the actual waste form, and then finally natural barriers, which is like granite or other rock or clay, or a very stable geological formation, which can ensure the isolation from the biosphere for the long term, as required by the decay time of the waste. This is a picture about the Finnish repository, which is in the most advanced form and likely to be open next year. So Finland is leading in this field to demonstrate that this final geological disposal is really possible. So finally, I only have the summary. The most important part that the closed fuel cycle with fast reactors can improve the utilization efficiency of natural uranium, and that some advanced fuel technology fuel cycle options can reduce the amount and the radioactivity of the nuclear waste. But deep geological disposal is required for all fuel cycle options, and that you just remember one sentence. I would suggest this last one, that the used nuclear fuel of today is a raw material or a resource in the fuel cycle of the future. So thank you very much for the presentation. Sorry if it was a little bit longer, and I'm ready for answering questions.
Thank you, Mate, for your presentation. Very interesting. And yes, there are several questions in the chat. I will start from the first one. And Evot is asking what solvent is used for the uranium leaching?
In the uranium leaching, it can be either an acid or a basis. It's practically carbonic acid usually, or a very light solution of sulfuric acid.
Okay, then there is a question from Marian, and he asks, the location for leaching are already known, or this is a type of reprocessing?
I don't know this. I understand this exactly. Like Kazakhstan is the biggest producers of uranium right now, and the production from Kazakhstan is all from in situ leaching. So like you have many mines in Kazakhstan and in some other places of the world where in situ leaching is going on. If that was the question.
Then, if not Marian, you can unmute yourself.
Good afternoon. My question was actually regarding if we know the locations of these ones or they're just randomly selected. I assume that they do some type of digging to know if there is that type of ore, like uranium, is available in that.
Yeah, obviously there is a geological survey before they start leaching. Like even in Hungary, we had decades ago some mines, underground mines. And recently, as there was some rise in the uranium prices, some Canadian companies appeared and started to investigate whether it's worthwhile to start in situ leaching because it's much cheaper. But finally, it did not start it. But it's definitely first you need to have a geological survey whether the uranium is there or not.
All right, but then if we come back to the previous question with the solvents, won't these solvents also affect the, let's say, purity of the ground and then affect also the life, like the, I don't know, the birds, the underground waters? Won't it infiltrate those?
Definitely. This is the major environmental concern with in situ leaching. There are very bad examples back from the Soviet times in the Czech Republic that the remediation of the efforts are still going on after in situ leaching mining in the 60s. So it needs to be very closely monitored. It needs to be in between watertight layers. there must be monitoring wells, that it's not spreading toward the to drinking water or the water basis in the environment. So it's true. It can be done in an environmentally safe way, but there are risks. It's true. Yes, I would suggest, I mean, it's a long-term thing, but uranium prices must increase even in the short term, not because of the lack of resources, but because the production capacities in mining right now is just enough for the consumption. And very soon they will need to open up mines, which are more expensive than the present mines. Nowadays, because of the cheap uranium from Kazakhstan, many mines are closed, which operates on higher prices. But in the next decade, like it's quite sure that there will be some increase in the uranium prices. With the laser enrichment, yeah, laser enrichment. This is a very good comment. This is really one of the concern with the laser enrichment, that it can be smaller size also than typical centrifuge farm, and less energy and so on. And even the separation efficiency is much higher, so it's easier to produce higher enrichment than with the current facilities. So there are concerns with safeguards, so the proliferation of nuclear materials, but I think the international regime on safeguards can ensure also this. So if these facilities are under control in the same way as nowadays every nuclear facility, then I think it can be ensured that no material will come from these to illegal uses.
Okay, I don't see more questions for now. So thank you very much, Mate, for your thorough presentation and answer. And let's see tomorrow. So finally to talk about generation for reactors. So
yeah, and, thank you very much for your
thank you again. So now let's go on and let's start speaking about dosimetry. And now the next speaker will be Richard Mitiko, and I already see he's with us. Good afternoon, Richard.
Good afternoon.
And when you're ready, you can start sharing your presentation.
All right. So there was a bit of a mix-up here. I was told that my presentation would be about radiation protection. So I made my presentation about radiation protection. But still, since in the second half, so first half will be a presentation, and after it, there will be a laboratory practice. The latter part is shorter than the allocated time. And at that point, I will have time to answer some questions about dosimetry. In the meanwhile, I will share my presentation if I can find it. There it is. Since I was told that we should try to make it as automatic as possible, so I made my presentation supposedly play itself. We'll see if it works. So don't be surprised if you hear my voice and I'm not talking. And let's see if it works. Gyors billentyűk.
So, Richard, there should be an audio. It's supposed to be, because we cannot hear the
presentation itself.
Yes, we can see it perfectly full screen, but we don't hear any
sound.
Audio.
All right.
No sound.
I'm not exactly sure how to handle this, but all right, then I will just say it. Just a moment.
Sorry, there is an option when you share that you share also the sound. when you start sharing among the
share computer sound. I
Yeah.
found it. So thank you. Sorry about that. And let's try it again. Good day, everyone. My name is Richard Miletsmitko, and I'm here to give a presentation about radiation protection. For starters, let's go over the principles of radiation protection. At the point of justification, first we check if what we are trying to do is allowed or not. For example, mixing radioactive material into food or children's toys is simply not allowed. Then, we check if what we are trying to achieve can be achieved via other methods, which are less drastic. Then comes dose limit. This is basically drawing a line in the sand. If this dose limit is exceeded, then someone is probably getting sued, unless certain conditions are met. For example, if what you are trying to do happened while you are trying to save lives, or trying to prevent a disaster from happening. The final point is optimization. Here, first we estimate just how much dose one would suffer while doing a certain task. Then make plans to decrease this exposure as low as reasonably possible. Reasonable being the keyword here. Based on these estimation and planning, we have international recommendations regarding dose limit, one of which, the recommendation of the ICRP, can be seen here. People are put into two categories: public, also called civilians, and workers. The idea here is that workers are getting paid to do this, therefore higher doses/risks are allowed. Also, you might have noticed that there are different dose limits for different body parts. The idea here is that if we only limit one dose, for example, whole body dose, then certain body parts, for example, the eyes or the hands, so on and so forth, may receive much higher dose, and without the limits, this would go unnoticed, which could have severe consequences. I think it's important to place just how dangerous radiation actually is. One way to do this is if we check its dangers compared to something that people usually do, for example, smoking. Here we can see the result of research done by the Japanese Radiation Effect Association. If we compare being exposed to 100 millisievert to smoking 20 cigarettes a day, then we can see that smoking is actually more dangerous. Once you start researching risks, then you can run into data collected by insurance agencies. They collect a lot of data and compile them, which is not really surprising considering that for them knowledge about the risk is money. But still, how they represent them is not necessarily all that helpful. I mean, what does smoking actually entail? Does this mean that I have a single cigarette a day? Does this mean that I smoke an entire pack a day? We don't really know. And don't even ask me what being unmarried actually refers to here. I think the two datasets shown here demonstrate that being a radiation worker or being exposed to a low level of radiation is not really that dangerous. Of course, if we exceed the limits previously shown, or if we actually reach the threshold of radiation sickness, which is around 250 to 500 millisievert, well, things change drastically. I think it's a good idea to give an example about optimization. In this example, we have a source placed somewhere, and we are trying to build shielding between the source and the personnel. The damage, or rather the cost of the damage, increases linearly with dose as per the stochastic effect of radiation. This can be seen with the red lines. Now, for shielding. The shielding, or rather the cost of the shielding, increases exponentially as we try to decrease the dose as per the exponential attenuation law. This cost is represented by the green curve. Now, if we add the cost of the damage and the cost of the shielding together, we get a curve that has a minimum point. At this minimum point, we have a dose, and this dose becomes the dose restriction. The dose restriction could be potentially exceeded, as in it can happen without any real serious consequences. When this happens, the entire optimization is usually checked again. We see if the dose estimation is correct. We check if the shielding is actually sufficient. We do things like that and figure out what went wrong. And if it is not really the fault of the worker or anything like that, then we simply do the optimization again. One might question just how ethical it is to just assign a number to getting damaged by radiation, but this is a matter of economics. So economists and medical doctors and other experts came up with numbers regarding just how much radiation damage actually costs. Of course, this can change. Therefore, we have different lines for different estimations, as can be seen here. Now that we have an idea of what we are trying to achieve, it's time to go over how we are achieving this. There are three main methods to decrease those. First is limiting time, second is increasing distance, and the third is using shielding. When it comes to limiting time, it seems fairly simple, and a good example can be seen in the series called Chernobyl. In this, we have a scene where they are on the rooftop and they are trying to clean it, and they are using people to do so. And every person is given 90 seconds, as in you go in, you work for 90 seconds, and when this time is passed, then you can throw everything away and run back. In fact, you have to do this. While this is a good way to decrease individual dose, doing this and changing people increases the collective dose. So it's not as simple as limiting time is good. When it comes to distance, the idea is simple. The further you are from a source, the less dose you receive. If we have a point source and we are in vacuum, then this is the inverse square law. Now, if we are in a field of radiation, there are generally two things we want to do. One, we try to measure it. The second, we try to manipulate the source somehow. When it comes to measuring, we can use detectors that are attached to an end of a rod, which can be telescopic or a simple rod, or we can use something with a long cable, for example. If we try to manipulate it, then it can be something as simple as a tweezer or some long-reaching manipulator or things like that. You can also come up with some remote-controlled device. However, these generally require electronics, and electricity and ionizing radiation not always play nice together. There are all kinds of materials one could use as shielding. One way to describe just how effective something is at attenuating radiation is their half-value layer, HVL for short. Half-value layer is the thickness of the material required to weaken a certain radiation to half its intensity. On the top right, we can see a table containing the HVL values of different materials. Unsurprisingly, lead is very good at attenuating gamma radiation. However, one should remember that power plants are not built of lead. Why is that? First of all, lead is very, very expensive. Second, lead is not really as mechanically sound as, for example, concrete, so you can't really build buildings out of lead. And third, while it is very good at attenuating gamma radiation, neutrons go through fairly easily. In the middle table, you can see HVL values at different energies. Unsurprisingly, if the energy of the radiation increases, the HVL value increases as well, showing that it's harder to attenuate the radiation. In the bottom table, we can see HVL values associated with shielding against strontium-90, showing that it is much easier to defend against beta radiation than, for example, gamma. When it comes to radiation protection, it's important to note what kind of exposure we are trying to protect people from. There is external exposure and internal exposure. External exposure is when the source is located somewhere outside the body. And internal exposure is when the isotopes themselves get into the body. When we are talking about external exposure, we should further differentiate between exposure that comes from a source that is just somewhere far away and exposure that comes from the material that is located on your surface, that is your screen or your clothes. The reason for this is that if it is located on your surface, then it can very easily become internal exposure. I would like to mention some terminology as well. If something has radioactive material on it, or something has radioactive material in it, for example, a table soaked up the radioactive liquid, that is called contamination. If a living body has some radioactive material in it that was not planned to be there, that is called incorporation. When it comes to shielding, there are two ways to have it around you. One is to actually wear it. The idea here is that if it is on you, then there is no way to actually step out of the protection. The problem with this is that protection is generally very, very heavy. For example, a lead apron that has the same protective value as 0.5 millimeter of lead can weigh up to 20 kilograms. The other way to handle shielding is the one people usually think of when they hear the word shielding. That is to build a shield. It can be built into walls, for example, or you can take interlocking lead bricks and build a wall yourself.
This outside shielding can also take the form of not actually walls. It can be, for example, a containment unit, which is basically a box with usually one transparent side. You can also have something like an L-block shield, which is basically a one-directional defense. If the source is behind it, then you are safe. They have the advantage of being fairly mobile, as in you can pick them up and place them elsewhere. And also you can reach around, which is very good when you are trying to manipulate something. Things like this are usually found in a laboratory. When it comes to internal exposure, we are not really using shielding in the traditional sense. We are more like wearing protecting gear. This can be something simple like a lab coat, gloves, a simple mask, some glasses, things like that. However, if we are dealing with something fairly nasty, then we can up the ante with wearing gas masks or maybe a spacesuit-like defensive gear. You can also resort to containment. This is typically done via a unit called the hot cell, which has things like manipulators inside them, maybe some chemicals, slots for putting different things in, and very importantly, they have ventilation. Ventilation can be also applied to a room. This way, if you have some radioactive material that is floating around in the form of a powder, form of a gas, things like that, then it gets just sucked out of the room. Once the radioactive material is in the ventilation system, there are generally two ways to deal with it. One is to just throw it outside. This way, you got rid of it, however, the environment might get damaged. The other way is to install some filters/absorbers that soak up all the radioactive material. All these tools are nice and all, but they're worth nothing if you are not using them or not using them correctly. That's why the greatest defense of all is to follow the rules. The rules, however inconvenient they might seem, are usually there to protect you. The lab coat can get very hot, but if you have it, then you don't get contaminated on your skin, for example. Not touching or while using your hand to place a source might seem inconvenient, but this way your hand dose will be much lower. Documenting just how much activity you used in a certain procedure might be a pain at times, but this way if you pour it on the floor, you know just how much danger you created. All of this is to say that following the rules, as in the written word, is a very good idea. And that's why paper is one of the best radiation protection material. Of course, the ones writing the rules can't think of everything. Usually there are holes. That's why you should use your head as well. Use some common sense. For example, you don't pipette radioactive material with your mouth, even if it is not in the rules. As previously mentioned, contamination is when radioactive material gets somewhere it shouldn't be. We can talk about external contamination when it's on the surface, and we can talk about internal contamination when it gets into the object or the person. Well, that depends on what kind of state the material is in. In physical sense, is it solid? Is it a liquid? Is it a gas? Is it hot? Things like that. But also, it's important to know what kind of chemical properties does it have. Also, a lot hinges on what gets contaminated. Is it an object or is it a person? Getting rid of contamination is called decontamination. There are several tools that one can generally use to get rid of contamination. However, it is smart to go with increasing severity. You start with something simple, for example, a paper towel. You try it, it didn't work. Then you go with a wet towel. You try it still didn't work. At this point, you might go for a brush, then a wire brush, maybe you can try acid, things like that. While doing decontamination, direction matters. Generally, you try to collect the radioactive materials. That's why if it's on a horizontal surface, then you sweep inward, so to speak. And if it's on a vertical surface, for example a wall, then you go from up to down. In this way, even gravity will be on your side. Of course, humans are special, or to be precise, living things are special. When it comes to them, you can just use anything you want. For example, acids and wire brush are off limit. Even hot water is a problematic thing because it opens up pores, allowing radioactive materials to get down under the skin. Also, things like the inward motion are not always applicable. For example, if someone has a wound on their body, then you can't just sweep everything into it. If anything, you try to clean it out. Same goes for example, the eyes, because you have tear channels there and you have the eyes themselves that are an entry channel into the body. If something gets into the body, then it generally tends to stay at least for a while. Different materials react differently. You can use certain chemicals to speed up this process. For example, if it's something like tritium, then it's enough to just drink more water, or you can go for beer. However, there are materials that get built into the body, for example, gets into the bones, and it's very hard to get rid of them. For example, strontium-90 is such a material. Usually, when it comes to internal contamination, as in incorporation, medical doctors get involved. The reason for this is that at this point, you have to issue drugs, and that's not something that physicists are really experts in. In case of incorporation, there are some things that you can do to measure just how much get incorporated. You can take samples from blood, from urine, from skin, from hair, things like that. Also, there's the thing so-called whole body counting, when you get logged into a room and a very sensitive detector measures how much radiation comes out of you. And this way, you can give an estimate of just how much got into you. Here we can see an example of a decontamination kit. Decontamination material, as in things that are used for decontamination, generally get pooled together. This is called a decontamination kit. Most countries have laws that describe what you have to have in these kits. These are the minimal requirements. You can always have more. They generally have the previously mentioned chemicals for cleaning, some protective gear, and even things to store the radioactive waste that gets produced during the decontamination process. When it comes to contamination detection, there are generally two ways. One is to have a gate. This gate can monitor people just passing through, or it might require you to stand in there and get a measurement. These get implemented at the doorways of laboratories, at the entryways of huge complexes like nuclear power plants, but you can find such gates on national borders as well. The other way is handheld devices. These can be a single unit, for example, the Radai AB100, or they can be a simple attachment to a more universal detector. For example, the FH40 has such attachments. When it comes to localizing the contamination itself on the body or the object, the gates can have pads where you place your hands and feet, which are usually the ones that get contaminated. They can also have several panels, each with their own detector, only measuring at a certain area. This way, if only just certain panels light up, then you can say that yes, we found the contaminant, it is around here somewhere. Handheld devices, on the other hand, can be hovered all around the body, similar to the panel method. You move them about, and suddenly they start lighting up. Then you move them a bit, they stop measuring radiation. This way, you can localize that yes, there is radiation here, and where's the radiation, there you find your contaminant. When you try to measure how much exposure people actually suffer, that's called personal dosimetry. It generally gets applied to workers. To do these measurements, you can use active and passive methods. Passive methods have the advantage of generally being cheaper, and they are generally more indifferent about what kind of radiation they suffer. The way to do this is to generally have some kind of crystal and use different kinds of shielding with the crystals to determine what kind of radiation you actually get exposed to. You can take the crystals and the shielding themselves and encase them, forming a single unit. Then you can wear this single unit on yourself. This is usually done when you are trying to measure whole body doses. When you are trying to measure a certain body part, or rather exposure of the body part, then you can take a single crystal or a more complicated unit and attach it to a ring or glasses. States can and have mandated personal dosimetry with passive detectors. In such cases, they usually appoint some institute to handle distribution and collection of the detectors and even the measurements themselves. What gets measured is usually collected into a huge database that the individual can request the information from. The second method of personal dosimetry is active dosimeters. In this case, you take electronic personal dosimeters, APDs for short, and mandate their wearing. Using such electronic devices has the distinct advantage of constantly measuring and generally allowing you to see what gets measured. This way, you can implement a warning system if someone gets exposed to too high dose rates or if someone suffers too much dose. On top of having a warning system, if you can see the dose that you suffered yourself on a display that you wear on yourself, that can have a significant psychological effect. Also, while using such devices, you can electronically log the data. I mean, you can do so with passive dosimeters as well, but this way you can make it automatic. When it comes to dosimetry, be it personal or otherwise, it's very important what kind of device you are using. As in, can it even measure the type of radiation your workers get exposed to? And if it can, is it in the relevant energy range? How accurate it is? Can it measure low dose rates? Can it measure high dose rates? If it can measure, how accurate it is? What is the dose rate at which point an active dosimeter gets fried, for example? Here you can see some examples. 2 personal dosimeters and 1 handheld device. The first personal dosimeter, the red one, is sensitive to photon, usually shortened to gamma, and electron, usually shortened to beta radiation. When it comes to photons, it has a fairly low minimum energy, therefore it can measure even X-ray radiations. But if it comes to beta, then low energy beta simply goes under the radar. The second personal dosimeter, the black one, is very similar to the first, except instead of electron or beta radiation, it is sensitive to neutron radiation. As you watch the energy range, you might notice that it is actually not sensitive to thermal neutrons. The third one is the handheld device. This one has a higher minimum energy, meaning that some X-ray and light gamma might go under the radar. It is also only sensitive to photon radiation. If you look at how much dose rate it can actually measure, you can see that it is much higher than the ones for personal dosimeters. The idea that this one is a more heavy-duty device, meaning that you expose it to much higher dose rates. When trying to figure out how much exposure one suffers, we can go past personal dosimetry and reach the realm of area monitoring. These are first and foremost done by devices that are installed into the room. They can be on the wall, hanging from the ceiling, built into the wall possibly. The thing about them is that generally they have a sensitive area, the volume that they are actually measuring, and they only don't know the dose rate of that one. You might use that number to describe the entire room, but that is merely an estimation. They may or may not have a display that shows what they are actually measuring, but even if they don't have a display, they almost always have a warning light and some sound system installed that issues a warning sound. Of course, there can be more to area monitoring than a simple gamma probe. There can be other kind of radiation, for example, neutrons at a nuclear reactor. On the left, such a neutron detecting device can be seen that is attached to a ceiling. Beyond measuring the radiation in a room, there might be a need to measure how much radioactive material is in a certain medium. For example, in the primary coolant loop of a nuclear power plant, or the air that is let out into the environment. The previously mentioned radiation monitoring gates can also be part of the area monitoring. They can be even used to restrict movement between different rooms. Area monitoring systems generally have a sort of nerve center, where all the information, all the measurements get sent into. Here you can implement different things. You can display the data, you can make warnings if something reaches a certain level. The warnings can be accompanied by warning lights, warning sounds, things like that. There might come a time when your area monitoring that is pre-installed is simply not enough. For example, there are new regulations that require new measurements, or you have periodic measurements that were simply not thought of when the installation happened. Area monitoring systems rarely have a plug-and-play system in place. Therefore, you have to rely on portable detectors. These can be simple handheld devices with attachable detectors, or maybe just a simple detector. At any rate, you can place them down on the point of interest and do your measurements. If it is something that have to be left there on a semi-permanent basis, then you simply leave it there. Radiation protection includes protecting the public and the environment, as was previously mentioned. Any significant action, such as building a power plant or other such high emission facility, is preceded by planning and modeling. The first step of this process is data gathering. We gather all kinds of data regarding the weather, the physical and chemical properties of the potentially released material, geography. We even consider the building plans. On top of collecting data, we also have to consider models. Models basically help us describe the reality in simplified terms. One such model is the Pascoli-Clifford stability class. This describes how material will behave in the atmosphere once emitted from a chimney, depending on the temperature gradient of the air. It does not cover all possibilities, there are only 5 classes after all, but it is sufficiently accurate approximation. The gathered data gets fed into these models, and the numerical results we get fed into bigger models. For example, we get data regarding the temperature gradients in the area. Based on this, we figure out which stability class our area is in. Then, this gets fed into a model which tells us how radioactive material will propagate in the area. There is a lot of data to be handled, not to mention there is a lot of calculations to be made. We generally don't do this by hand, we delegate the problem to computers. Nowadays, there are actually dedicated softwares that already contain a lot of data and models, so we just have to put in initial conditions, choose what model we actually want to apply, maybe give some extra information regarding the weather or something like that, and poof, the computer does all our work for us. Such modeling is of course not just used for planning when you are trying to build something. If something happens, for example something explodes, something gets emitted that shouldn't have been emitted, then the same methods apply. We do the same data gathering, modeling, so on and so forth, to figure out if we have to, I don't know, evacuate an area or not. Modeling is all well and good, but still there is more to environmental monitoring than that. For starters, even if we have a very detailed model that we are very sure about and it meets all expectations by everyone, we still have to check if the results are real. On top of that, if we try to, say, create a new model, we have to take measurements to validate it. Also, there are things like disasters and other unexpected events, and to notice them, we sadly have to take measurements. These measurements are usually done by environmental monitoring stations. These stations are usually installed all over the country, and they can be used for more than just radiation protection. They can be just a single probe out in the field, or they can be an entire structure with a probe, with wind direction and wind speed measurements, temperature measurement, pumps that suck in air through a filter, creating samples. They might even be able to analyze the samples themselves and display the results. Actually, the sky is the limit with these things. And that's all I intended for this brief introduction to radiation protection. Thank you for your attention.
So hopefully it wasn't too terrible. Sorry for the changing volume and such. I did not make the entire presentation or rather audio for it in one time. So any questions?
Thank you, Richard. Yes, there are some questions in the chat. There's one
I can see it. Just the border. Oh.
The first is from Mariam here.
Mariam, being unmarried, males from the days, so the threshold is being married. All right, I get the idea that you have to be married, but what did they mean by not being married? For example, you can have a life partner. It's basically the same as being married. And was it counted into this or not? I meant things like that. All right.
And there is a second question from Tobias. Yeah. How dangerous would you say is uranium glassware during normal use?
During normal use, considering that uranium is first of all something that decays very, very slowly, and in the glass you have very little uranium. It has some radiation, I'm not gonna lie, but this radiation is basically nothing compared to background radiation that you are normally exposed to. If we are talking about small quantities, for example, a ball or something. if you live in a house made out of this stuff, then you might have some problems.
Okay. Are there any other questions? Not.
I guess that's the no.
Okay, so I think we can move to have a short coffee break, just 15 minutes and back, and then we can go on with the laboratory as said before.
Laboratory.
So yeah, online.
Sorry,
laboratory.
I just hate the idea of online laboratory. At best, you can have a video or something.
Unfortunately.
But whatever.
Yeah. Okay, so see you at 4 p.m. I will say. Okay.
Okay.
4 o'clock.
See you.
Okay, we are coming back live after the coffee break. And now we will have the online laboratory, as said before, Richard Miles Mitico. So the floor is yours, and you can start.
All right. So once again, in my desperate attempt to avoid actually speaking in front of people, we made a video, and I will be providing commentary for it. And once again, I try to share it. And I did not open it because I'm stupid. All right, that's great. Let's share the screen. That's the easiest way. So here is the video, and it won't work because the sidebar will be there. So just a minute. Stop sharing and video. All right, and with sound. All right, and let us begin. Good day, everyone. My name is Richard Miles Mitico, and I'm here to give a practical laboratory lesson. Or, well, because this is an online event, I can't really do that. But we will try to do the next best thing. And that is me showing / narrating some videos me and my colleagues made, showing some basic experiments / practices regarding radiation protection. Let's do some decontamination. To decontaminate, first we need, well, something contaminated. In our case, this will be this paper towel that is put into this tray. We are using a paper towel because this is a fairly typical example. When you are working with radioactive material that can, well, contaminate things, for example liquids, then it's a good idea to cover as much surface as you can with disposable material, for example a paper towel, to make it easier to decontaminate. As for the contaminant, that will be this yellowish radioactive liquid. It is yellow to make it highly visible, which is good for practice, but even when you are working for real, it's a good idea to put some dye into your material if it is possible, or have it colored in the first place. I'm about to finish the contamination. We have just this one last big drop. And it's done. Once we have our contamination, first we measure it, as in we try to detect where it is. While it is highly visible, it's still a good idea to do so. I turn on the machine, the scale goes up and down as the machine warms up and then cools back down to basic levels. And then I start moving it. And there it is, the scale goes up, so there is something there. Unsurprising, I know, but still. So there it is. Once we are done with this, I turn off the machine and put it away to clean up the working area, to lessen the possibility of contaminating something else. I take the small piece of metal away as well. Alright, this paper towel is disposable, therefore we will just consider it radioactive waste. First you take a bag or something that you will contain the waste in, and you write the necessary information onto the bag. This necessary information is usually when the waste was created, what is in the waste if you can say it, what is the dose rate, things like that. You write it down and then you put your waste into the container or well bag. While doing this, it's a good idea to minimize the contaminated surface that can touch other surfaces. That's why I'm folding up the paper. This way the radioactivity is inside the paper and it's insulated basically. Alright, once this is done, I take a detector, an radii AB100, turn it on, and I switch the backlights on to make it more visible. You can already see a blinking red light, and you can see that the display colors, at least on the upper half, are inversed. This indicates an alarm, so there is something still there. I'm moving it about, hovering over the tray to figure out where the contaminant is. Unsurprisingly, it is where the paper towel was contaminated beforehand. By the way, the upper row shows the sum of the beta and gamma hits, while the lower row on the radii AB100 shows alpha radiation. So we can summarize that we have some alpha or beta or both contamination. We are done. I turn the machine off. Then comes another contamination monitor with a smaller area. It is an attachment to an FH40. As I said, it has a smaller area. So theoretically, the localization of the contaminant should be more accurate once I'm done with this. I move it about, jumping here or there to make it a bit quicker. And I found it. Yes, there it is. Alright, now I take a dry paper towel and try to clean it up, using inward motions to basically collect the contaminant. Once I'm done, this paper towel goes into the waste as well. Then I measure again. This time I measure less, meaning that I probably cleaned up some of the contamination, but not the whole thing. Alright. There it is. Now I take a paper towel and, well, pour some distillated water onto it, theoretically increasing its cleaning effectiveness. And I take this paper towel and try to clean up the area, applying some force as well. And trying to not really smudge the possible contamination, as in trying to not increase the area itself that is contaminated. That's also a key point. Although I'm folding the paper to possibly not contaminate myself. And it's done. Another bit of waste. And one more measurement to see if I was successful. And, well, we measure basically nothing, so contamination was successful. Everything is beneath allowable limits, so we are good. Now that we have done some decontamination, it's time to move on to a very favored subject of laboratories, shielding. We have an alpha source, a sheet of paper, and an aluminum plate. We'll be checking these materials, and later on others, how well they work against certain radiation. First, we measure alpha radiation. We measure in CPS, so count per seconds, without any shielding. My hand could be a bit steadier. So much movement at such close distances can alter the measured value drastically, sadly. Now we measure through a sheet of paper, so we have paper shielding, and it proves to be fairly effective. So paper indeed does stop alpha radiation. Now we check the aluminum and sheet of paper, and we get even less radiation. So the paper, while showing stopping most of the radiation, did allow some through, but the aluminum dealt with that. Alright, now we have a beta source. Once again we do a measurement without any shielding. And we get a fairly high amount of radiation out of this. Once again we do a measurement with combined paper and aluminium, getting a much lower value, so either the paper or the aluminium worked. Question is, which one was it? So we raise the source, and we raise the detector just a bit more, and yes. And we can see that we have drastically more counts. So it was probably the aluminium that stopped the radiation and not the paper itself. Here we have a gamma source and the gamma probe on the other side. That's the black cylinder. And we wait for the measurement, and here it is. So the dose rate, we are measuring dose rate this time, is around 10, 11 microsievert per hour with aluminum shielding. Now let's try with lead shielding. We go in from above. As we get closer to the detector, closer to the source, we see that it's 5.7, 5.6. So aluminum is about half as effective as lead. Here we have a neutron detector and soon to be a neutron source. It's a PUBE source. It's a mixture of plutonium and beryllium. The idea is that the alpha radiation of the plutonium causes beryllium to shoot out neutrons for us. We will try to come up with some effective shielding. We try with a sphere made out of paraffin wax. Alright, so we have our material, and it has weakened the dose rate from around 30 microsievert per hour to around 6, even less. So it's about halved the dose rate of the source. Alright, we remove the shielding, and alright, we found something that seemed to stop radiation, neutron radiation. Let's check how lead itself fares. We put a lead brick in and we see that it is far less significant to decrease. It is a decrease, but not that impressive. The reason for this is that neutron radiation is best attenuated by a material that has a lot of hydrogen in it. Because hydrogen has a very similar mass to neutron, it is very good at weakening neutron radiation. And lead, well, lead is very far from hydrogen in terms of mass. Alright, we remove the lead brick. Reminder, lead bricks are heavy. And we put in something far more effective, something that's already proven its worth actually. It's a brick made out of paraffin wax. Paraffin has a lot of carbon and hydrogen in it, that's why it's effective. We place it in. We make sure it stands there. This time it's not as white as it was previously. The reason for that is simply that it's dirty and it's very hard to get dirt out of wax. At any rate, this time we have a much greater decrease in dose rate. So yes, paraffin is better than lead for neutrons. Now that we have compared different materials and their shielding properties, it's time to move on to checking how a single material fares when it comes to attenuating radiation. Let it be lead. On the left, you can see an orange cylinder. It has a gamma radiation source in it. We remove the lead.
Jelzi, hogy a belső detektor és azt is, hogy riasztási szint fölött vagyunk. Ez ennél a detektornál éppen 50 mikrosievert per óra.
Now that we have successfully silenced the alarm, I can talk about what's going to happen. We have a black cylinder on the right. You have seen this one before. This is a detector. Between the detector and the source, we will place lead and see how well it fares as we put in more and more. First, we put down some things to stabilize the plates. Each plate is around 3 millimeters thick. Alright, it's placed. It's standing. Good. As you can see that the dose rate fairly drastically decreased the moment the plate was put into the radiation beam. We had our one plate, it's time for the second. And here it comes. Careful. Yep. Good. Alright. You can see that the second plate, while still decreasing dose rate, was not as spectacular as the first one, so to speak. Now you may wonder why we have an ever decreasing dose rate. Why doesn't it just skips into a new value? Well, the reason for this is twofold. First of all, third plate. First of all, the detector is using a moving average. When you are trying to measure radiation, you need to take not one, but several measurements, because it is a probabilistic function. So the probability of you measuring the same thing twice is fairly minuscule. And to deal with this issue, you once again take several measurements and take their average. When you are continuously measuring, you do this via a moving average. But when there is a sudden change in dose rate, for example, then this moving average takes some time to reach the, let's say, actual value. And even when it's at the actual value, you never see the same value, or well, you can see the same value, but the chance of measuring the same thing twice, once again, is very low. So because of its probabilistic nature, and because we are using a moving average, we can see that the detector is slowly getting to the point where it can, and then it has peaks and valleys. And one more plate. Now, as I said before, as we put in plates, we get less and less attenuation. This is also known as the exponential attenuation law. As we increase the material, or rather the thickness of the material, we get ever so weaker attenuation, because attenuation is done via fraction. That's why we have things like half value layers and 10th value layers, which is the thickness of the material that weakens a given radiation beam to half and tenths and so on to its strength. So if we put in a half value layer, then the dose rate gets halved, for example. If we put in a 10th value layer, then the dose rate gets to its 10th. All right, we are reaching fairly low dose rates now, but still, why not try to weaken the beam to basically background radiation level, which is around 100 nanosievert, or well, more like between 50 and 200 nanosievert per hour. But to do that, we will need a bit more lead. So let's bring out our old friend. Here it is. We put in this thick boy. And the dose rate plummets once again. And we have 90 nanosievert per hour. So anyway, it's around background radiation. So you see the final piece was fairly thick. We needed a lot more lead than expected, because, as I said, it was a fractional process. Once again, we are here.
Jelzi, hogy a belső detektor, és azt is, hogy riasztási szint fölött vagyunk, ez ennél a detektornál egyben 50 mikrosievert per óra. És hogyha
Once again, we silence the machine, this time with a bit more struggle. But this time, we will be using, well, actually nothing to attenuate the radiation. Before, we put in more and more lead to fractionally weaken the dose rate, in the end putting in the thick boy. This time, however, we are trying something else. So far, every time we put something in, things get better, as in dose rates got lower. However, this time we put in, next to the detector, 2 containers filled with water. And if you paid attention to the dose rate, then you can see that it's increasing, which is quite unusual, actually. The reason for this is fairly simple. While putting shielding material in means that radiation gets absorbed and scattered away from the detector, but if you place it unfortunately, then the put-in material actually scatters radiation into the detector. The same can happen with a person. So adding in extra layers might actually make the radiation stronger. This is also known as build-up. So we had a segment about decontamination, another about the shielding properties of different materials, and the third about the attenuation law and build-up at the end. I think that should suffice for this short, let's say, practical lesson, but just as... Alright, so this was basically the video. Hopefully it wasn't too terrible.
No, not at all. Absolutely. You made it very interactive, even if it's not in person.
I tried.
So
if you speak Hungarian or understand it, then you might have heard some familiar voices in the background. The reason for this is that we successfully actually muted the device that was supposed to give the alarm. So we had to cut it in afterward. Sorry, go on.
There is a question for you in the chat, Richard. So you replied directly only to me, not to the audience. So,
I fucked up.
Marian
All right.
has the contaminated material measurement is measured in what unit? So I received your answer, I think. So you can reply now.
All right. So yes, the first device was measuring in CPS, count per second. And when you are trying to measure something that is unknown, and as this was practice, we say that it was unknown, you should measure in CPS or CPM, count per minute, or something like this, because it is a very general measurement. If you are measuring with becquerel or becquerel per centimeter squared or something like this, there are devices that can do this. For example, the Radai AB100 can do this in the first place. But when you do this, then the sensitivity might not be as high as it actually should be, because these becquerel values are for a certain source. For example, let's say cesium or cobalt or something like this. And if you are measuring something that is not this cesium or cobalt or something like this, then the becquerel values will be false values. And this might give you a false sense of security. So I think that answers that.
Thank you. Are there any other questions?
I think not. So at this point, I know that this was supposed to be about dosimetry. So I can try and talk about it or answer some questions about it, or we can skip this part and get on with the already delayed presentation that comes after me.
I don't know, because really we are a bit out of time. It's
That's
not
fine.
really urgent problem, but we have no more 10 minutes, I think. Then we have to move to the next presentation. So
All right.
I don't know if it's enough to.
Easier for me.
Okay.
Then I think that's it for me, and have a nice day.
Okay, thank you very much, Richard. Thank you again. And now the next online laboratory is with Gergely Orosz. Welcome, Gergely. I see you.
Hello, hello everybody. Good afternoon.
Okay, we can hear you as well.
Okay, super. Can I try something new out? Watch together. Do you understand or familiar with this web page? This is specialized to watch synchronized videos. So if I share this link in the chat, if you join to this, I think you will be
And watch together.
yes, I see as some of the users. And you can see my screen also. Oh, super. The students are viewing. Yes, and everybody can stop and start the video. So please wait for everyone, and do not use the sidebars, and watch together this short 18 minutes video.
Okay.
Okay.
But we cannot hear the audio, Gergely. I don't know if you have to share the sound as well when you're sharing the screen on Zoom, probably.
But if I stop the sharing and you are watching just the YouTube video in the watch together, there must be a sound.
Okay. No, okay, yes. I had the second device is muted, sorry. Yeah, okay, it's working.
Okay, it's working. Oh, super.
Yes, it is.
Because in this case, we can see it in HD or at least not in a play of the pixels. So how many are in this room? Many. Okay. I think we should start. Okay.
Okay. So let's.
All right. Thank you. Okay, I think everybody watched this video, and thank you for
very,
that.
very interesting. Just 1 second, there is some echo. Okay. No, it's very interesting. Congratulations also to your brother for the editing of the video. And then, yes, Marian, there is also a link on YouTube. So if please...
I shared the link a little bit up here.
Yes, maybe because of Marian logged in again later, so probably...
Okay, I will share it again. And
okay, perfect.
Copy paste it in the position. All right.
So it's on YouTube, and Marian, whenever you want, you can watch it. Now it's time for a question, if there are, from the audience. So please speak out or write down if you have any question for Gergely.
I wasn't able to completely follow. So you had the large local phases. The first one is the blowdown, and what happens after that?
After that, in this video, I forgot to mention it. This is my first video, so it has it's full of thoughts. So in the throttle, we cannot simulate the other 3 phases of the local. The first is that's the blowdown, when we discharge the system, and the other 3 is basically based on the emergency cooling system, and in throttle there is completely missing. So it's we have no hydro accumulators or any kind of emergency cooling system, and therefore the blowdown is the only phase which we can see in this video.
Okay, thank you.
It would be better if I highlighted it. But thank you for your comment, and maybe I will fix it.
Are there any questions? If not, in the meantime, Gabriel, you can also write down your email. Maybe if someone has any question or comments to send you.
Okay.
Always in the chat. So in the meantime, I will, if there are no more questions, I can call for a short last coffee break for today until 5 o'clock. We thank you again, Gergely, for this really interesting interactive video presentation. And if you have any question, you can write him whenever you want, and then we will see at 5 o'clock with the last quiz session for nuclear energy. So see you in 15 minutes. Thank you.
Okay, thank you. Bye-bye. Welcome everyone to this seminar. I am
So we are approaching to the last quiz session. I just remind you that the results you see today, we have not the final results of the whole quiz sessions we had together. So it's just the results of today's quiz session. You will have the final results only on Friday during the closing ceremony and the award. So don't consider that as the final ranking, the one you saw later. So I already sent the link. I saw there was also someone that logged in a bit later, so I'm going to reshare the link to join the quiz session. Okay, it's here in the chat. Please register yourself. And okay, I see they're almost full in the waiting room for the quiz session. We should have up to 22, 23 people today participating. Few are missing. And waiting a bit for the last participants. I just quickly recap you the tomorrow's program in the afternoon for the nuclear energy program. So we'll start with 3 lectures. The first again with Professor Mate Siebert, this time about generation for reactor types. Then we'll have a lecture about how the nuclear reactors in the future will look like. And then finally with Georgi Pokol, a lecture about nuclear fusion and energy production. After the first coffee break, we will have 2 laboratories, one together always with Professor Pokol about, with a plasma tube experiment and question and answer session on nuclear fusion, and then a laboratory on reactor operation. And then after the coffee break, there will be no more quiz. So this is really the last quiz session. We'll have an interesting event online, career guidance, and I warmly invite you to join tomorrow at 5 o'clock. We'll have a roundtable with international nuclear experts and professionals. They will be there to answer all your questions about nuclear careers and your expectation. They will be there to share their personal experience, to give you inspiring ideas and so on. So get this opportunity. It's very, very interesting, and will be tomorrow afternoon at 5 p.m. after the daily lectures and laboratories. So let's see. Okay, we have 22 people. I think we are all in. I'm going to share my screen. I invite you, as usual, to follow your screen and the link you joined the quiz. I'm just sharing on Zoom for the recording. Just 1 second. Okay. Now you should see also my screen, but we are all in, so we are ready to start for the last nuclear energy quiz session. There are no more messages in the chat. Okay. So let's start with the first question. What is the optional shielding material against neutron radiation? Material with high hydrogen density, material with high electron density, material with high mass density. There is no significant difference between materials. As usual, 25 seconds to answer. 3 seconds left. Okay. Everyone has voted, and the correct answer, as we saw, yes, is the first one, material with high hydrogen density. Let's move to the second question. Number 2. What is half value layer, HVL? As we saw before, is the thickness of material required to halve the dose rate of radiation, the thickness of material required to halve the dose limit, the thickness of material with equal attenuation of 0.5 millimeters of lead, or the thickness of material with equal attenuation to 0.5 millimeter of water, liter of water, sorry. Everyone has already voted, so, and the correct answer is the first one. So the thickness of material required to halve the dose rate of radiation. Next. What is the first step when we try to figure the environmental impact of a significant radioactive event? Data collection, modeling, verification, measurement, or doing the action? So what to do? Yes, the correct answer is data collection. Question number 4. What is incorporation? Radioactive material getting into the body, radioactive material getting into the body in a not planned manner, radioactive material getting onto the surface, or radioactive material getting soaked into wood. Five seconds. It was quite tricky, but the incorporation is radioactive material getting into the body in a not planned manner. So the correct answer was the second one. Then question number 5. Which is not a principle of radiation protection? An intrinsic property of the moderator due to its boron content. Oh no, I'm sorry. I'll delete this one. It's my mistake. So you are free and you can no reply because I had a bug with the program today, and the answers are not correct, are related to an old question. So I'm sorry, it's my fault. Will not count this one. It was the definition of the Doppler effect we saw yesterday. I had some technical problem in the morning. So let's move to the 6th question. What is the final product of uranium ore processing? A yellow cookie, yellow cake, white powder, or brown sludge? Everyone has voted, and yeah, obviously is the yellow cake. Congratulations. Let's move to the question number 7. Which enrichment technology has the highest share in the present day's industrial production? Electromagnetic, diffusion, centrifuge, or laser? So the most common enrichment technology is the centrifuge. Congratulations. Question number 8. What reactor physics condition provide the highest breeding ratio? U-233 fissile material in thermal neutron spectrum, plutonium-239 fissile material in thermal neutron spectrum, uranium-235 fissile material in fast neutron spectrum, or plutonium-239 fissile material in fast neutron spectrum. 2 seconds left. Everyone is voted already. Okay. And the correct is the last one, exactly. Plutonium-239 fissile material and fast neutron spectrum. Let's go on question number 9. What is the MOX fuel? uranium-plutonium containing oxide fuel, molybdenum oxide-based experimental fuel, major and minor actinide containing oxide fuel, and oxide fuel using uranium-235 and plutonium-239 in the same proportion. So today with Professor Mate Ibert. Quite balanced, but the right answer is the first one, uranium and plutonium containing oxide fuel. Question number 10. What is the typical planet time scale for temporary storage of spent nuclear fuel? 5 years, 25 years, 50 years, or 150 years? Temporary storage of spent nuclear fuel. The typical planet time scale is exactly 50 years. Congratulations. Let's move to the second half of the quiz. Question number 11. What does CANDO stand for? With CANDO reactors, Canada does unbelievable reactors, Canada deuterium uranium, and Canada uranium reactor. Okay, everyone has already voted it. So yes, it's Canada deuterium uranium, the correct answer. CANDO stands for. Let's move to the next one. What kind of fuel the CANDO reactors use? So, with heavily enriched uranium, with natural uranium, ceramic type, or plutonium. So it's very clearly this afternoon. Everyone has already voted again, and yes, with natural uranium is the correct answer. Congratulations. Next. What is the main advantage of the CANDO type reactor? It is so online refueling, can be placed anywhere, does not produce any waste, or can be operated without experience. One has voted again on time. You're specialized in CANDO reactors, and yes, exactly. It's online refueling, the main advantage of the CANDO type reactors. Let's go on. Number 14. What type of coolant the CANDO reactors use? Tap water, heavy water, light water, or molten salt? Well, it's two answers missing. Okay, everyone has voted. And yes, it's heavy water. The correct answer. Then let's see, question number 15. How do you recognize a CANDO type reactor among these four? So the letter A is placed horizontal, the B is placed vertical and has one steam generator, the C uses salt as coolant, and the D, it is in fact a very high temperature reactor. Yes, exactly, the first one, it is placed horizontal. In this picture you had, showing the main characteristics of the CANDO reactor. Then, what is the probability of occurrence of a LOCA accident? As we saw in the last presentation, one of these is the probability of loss of coolant accident. few seconds left. Okay, and everyone is voted. And I'm sorry, but the correct is the second one, the second option. So no correct answer this time. Let's move to question number 17. Which of the following statement is true for large break loca? So coolant loss balanced by normal makeup system, low depressurization and gravity-dominated separate flow condition, rapid depressurization, turbulent homogeneous flow during blowdown, or secondary side required as a heat sink to depressurize primary system. So the true one is the third one. Congratulations. Rapid depressurization, turbulent homogeneous flow during blowdown. Let's approach to the end of this quiz session. Question number 18. Which of the following emergency cooling systems works passively in a VVR 440 reactor? High pressure injection system, hydroaccumulators, low pressure injection system, or containment injection system, sprinkler? One of these. Time is up, and the correct is, yes, exactly the second one, hydroaccumulators. Congratulations. Question number 19. How do we heat the fuel rods in the Trackle facility, as we saw in the video? With electricity, with nuclear fission, with hydrocarbon combustion, or with geothermal energy? In the video of Gergely Oros, the Trackle exercise. Everyone has voted. And yes, the correct answer is the first one, with electricity. Last question. Which of the following nuclear accidents can be linked to a small break loca? Fukushima, 3 Mile Island, Chernobyl, or Tokaimura? Okay, everyone has already voted. And yes, the correct one is 3 Mile Island. Congratulations. So let's see the final leaderboard only for today's session. Then I have to recalculate and to delete. I saw the only 2 correct questions for the question number 5 that was wrong. So we will not count that one in the final result. I'm sorry again. It has been my mistake. So let's see the temporary leaderboard for today. First place for Tobias, congratulations, followed by Ivo, Ivan, Senia, and all the other participants. Congratulations to all. So this was the last quiz session for the nuclear energy as well. This morning we had one for the medical physics. I'm stop sharing my screen and moving to switch on my camera. Okay. So the quiz session is over. Thank you all for your participation. I hope you enjoyed all this session during these last days. So we have again one day tomorrow with lecture, laboratories, and the very interesting online event at the end of the day. I invite you again to join after the laboratories at 5 o'clock, and then Friday we will have the closing ceremony and the award. So thank you all again, and see you tomorrow. Have a nice evening. Bye.
Thank you. Bye.
Thank you. Bye.
Goodbye.